yourselves with that. Okay, I hope this is clear. So let's begin. So the first paper is called Synthetic Acoustic Image Generation for Audiovisual Localization.
Hi, I'm Valentina Sanguinetti and I'm presenting Synthetic Acoustic Image Generation for Audiovisual Localization. Acoustic signals acquired by an array of microphones can be combined with the beamforming algorithm to produce acoustic images, which can distinguish the spectral signature of sounds coming from different directions in space. They allow to localize sound sources better than mono and stereo audio. However, acoustic images are typically generated by microphone arrays, which are not so widespread. To exploit this empowered modality, we propose to reconstruct acoustic images from a standard video. In this way, even without an array of microphones, we can reconstruct the spectral signature of the sounds associated to each considered direction. To this end, we propose a new model based on UNet and VAE, trained to reconstruct acoustic images from a single microphone audio enriched with the visual content of the scene. Then, we perform audiovisual localization by estimating the energy of sound from synthesized spatial audio. Our method generalizes better on localization tasks than previous state-of-the-art models on unseen datasets. We name our novel architecture UVAE, as it is a hybrid of a variational autoencoder and a UNet. UVAE is trained to reconstruct acoustic images feeding audio and relative RGB frame. The single microphone audio was provided as male frequency subtle coefficients representation to simplify the generation task, because acoustic images to reconstruct were compressed using male frequency subtle coefficients. Using ResNet 50 pre-trained on ImageNet, from the considered image we get a visual feature map to concatenate to the audio encoder, in order to provide the spatial cues which are missing in omnidirectional microphones. We assess the quality of reconstruction of our UVAE, considering acoustic images ground truth. Our metrics include mean square error, GAN-test and GAN-train, which measure faithfulness and diversity of generated samples by means of classification. GAN-test measures the accuracy of a classifier trained on real samples and evaluated on generated ones, to quantify semantic similarity to real samples. GAN-train measures the accuracy of a classifier trained on generated samples and evaluated on real ones, to capture the diversity of generated samples. Then we evaluate both quantitatively and qualitatively audiovisual localization. We consider two datasets containing acoustic images, audiovisual indicated actions and acoustic images and videos in the wild, and two datasets containing videos collected from the Internet, a subset of Flickr SoundNet and VGG Sound dataset. As regards localization, on ACIVW dataset we have a better result than on AVIA because we have more data and less noise. We tested our models on Flickr SoundNet testset. This dataset includes ground truth bounding boxes to evaluate localization. Our ACIVW model performs better than methods which were trained on more videos second of audio and classes than ACIVW dataset. So our model is more efficient, as it generalizes better to new datasets, even if training using a dataset different from the testing, including only 10 classes. As regards ACIVW dataset, the energy of our reconstruction is very similar to the energy of acoustic images, if we compare it to the real test samples. As it can be noticed from the both, the reconstructed energy is sometimes even less noisy than the ground truth one. AVIA dataset is a more challenging benchmark, not only because of noise present in some scenarios, but also due to the periodicity of considered sound. In some frames, we do not have any sound, but only background noise, such as in the first row on the left, where the boy is about to clap, so that it is difficult to match sound and video. We show some results of estimated energy by AVIA and ACIVW models on Flickr SoundNet. The ground truth location of sound sources, which are bounding boxes, are not precise, as they are larger than the region from where the sound is coming from. Therefore, we suggest that acoustic images' energy can be better to evaluate models, taking into account that they represent physically from which point the sound is coming from. To evaluate our models on real videos, we test them on VGG Sound dataset, for which we can only show some qualitative results. We consider a subset choosing classes similar to those considered at training time. The estimated energy maps are very realistic, even if belonging to a completely different dataset never seen during the training. To conclude, in this work we have proposed an architecture to reconstruct acoustic images from standard videos, without the use of arrays of microphones. The synthetic samples allow performing audiovisual localization in a novel way, exploiting estimated energy of sound, providing a more accurate sound source localization than recent methods based on the correlation between audio and video data. Thank you.
So this was the first paper. Just a reminder in case you just logged in that we will have Q&A sessions every 4 papers. So this was the first one. Moving on to the second one, which is called Post-Controllable Talking Phase Generation by Implicitly Modularized Audiovisual Representation.
Hi everyone, I'm Hangzhou from the Chinese University of Hong Kong. Here, I'll introduce post-controllable talking phase generation by implicitly modularized audiovisual representation. First, let's watch a demo video that is created by our method.
We present post-controllable audio-visual system, which achieves arbitrary subject audio-driven talking phase generation with free post-control. We take an arbitrary image as identity reference and drive it with a clip of audio and a post-source video.
While there are a number of studies tackling the task of talking phase generation, a few problems remain. Many of these methods rely on intermediate representation, such as 2D or 3D landmarks. These representations can be not accurate under extreme cases. On the other hand, pure reconstruction-based methods can rarely change pose. Moreover, no method has shown the results of free pose control under large views. To handle the challenges above, we take the inspiration from a phase reenactment work, which shows that identity information can be repelled by frame augmentation. And furthermore, the style-based generator can automatically balance identity-related and non-related information. It can serve as a strong backbone for our framework design. Based on the discussions above, we designed our post-controllable audiovisual system as shown here. 3 latent spaces, namely the identity, speech content, and pose space, are modularized. While the identity space can be easily encoded with ID supervision, it is difficult for the others. Thus, we propose to encode a non-identity space for easier feature learning. It is achieved by performing 3 types of frame augmentation. The intuition is that this non-identity space can serve as a source for desired speech content and pose information. Afterwards, by adding an MLP, the speech content space can be encoded through contrastive learning with softmax contrastive loss, mapped also from the non-identity space, with the implicitly devised a 12-dimension postcode without any constraint. Finally, the features from the 3 spaces are concatenated and sent to a StyleGAN2-based generator. The reconstruction loss implicitly enforces the postcode to learn the desired information. This is the whole pipeline of our work. We have evaluated on several numerical metrics, and please watch our demo results.
Listen, I will be more ready than I was in 2012 because I will have done my job for longer and hopefully gotten better.
Well, I'm 40 next year, so I thought that it might be a good idea.
We got to get Pat in front of everybody. We got to get Pat in the thing and whatever. And I just think that our music has resonated much higher than my face, which is totally cool now.
At the end of the day, you just try to keep it in perspective and again, just come home to what your reality is. And
the brightest. And tomorrow the fashion police will report on your dress and who wore it the tightest. If you win, have the time of your life. Tell your manager, dad, and your mom thanks. Hi to your kids and your husband or wife, maybe just for the hell of it.
Big commercial hit, and what it did was it put racism on the breakfast table. It made people examine their own bigotry.
To conclude, we leverage audio-visual synchronization for cross-modal synthesis and the disentanglement of pose information. The style-based generator helps information balancing through reconstruction training. Thank you for watching. The code and models are available on our webpage. Hi everyone, I'm Hangzhou from the Chinese University of Hong Kong.
So moving on to the next paper, its title is Self-Supervised Learning for Cross-Modal Retrieval based on Sound Category and Location.
I am Tomoya Sato in the University of Tokyo and talk about our research, self-supervised learning for cross-modal retrieval based on sound category and location. In recent years, videos with multi-channel sounds are widely spread. This is one of the examples. We can see trumpet player on the left side of the screen, and we can also hear trumpet sound from left. As in this example, videos with multi-channel sounds contain both category and location information for sound sources. On the other hand, existing self-supervised methods learn only sound category or location, and they do not fully utilize videos with multi-channel sounds. Our motivation is to propose self-supervised method based on sound category and location. Then we apply learned features to cross-modal retrieval on images and stereo sounds. Note that by using our features, we can perform retrieval based on not only sound category, but also sound location, in contrast to existing methods that are based on only sound categories. Our approach is to learn distance among image feature and multiple stereo sound features. We consider three types of stereo sounds for an image. First is matched sound, taken from the same video as image and has the same sound categories and location. Second is flipped sound, which is left-right flipped sound from the same video, which has the same category but flipped locations. Last is mismatched sound from different video, which has the different categories. Then, matched is placed in the closest distance to the image because it corresponds to the image semantically and spatially. Next, flipped is placed closer to the image than mismatched, because we assume semantic misalignment has greater impact than spatial misalignment. By introducing the order constraint matched, flipped, mismatched on the distances among image and sound features, the feature encoder can be trained to preserve both semantic and spatial information about the sound sources. This is the proposed network. Input is image and three types of stereo sounds. Sounds are converted to spectrograms. Image feature and sound features are extracted from image and sound CNN, and they are input to the proposed loss function to realize the order constraint among the features. We propose a novel loss function, stereo sound ranking loss, based on triplet loss. By these following equations, stereo sound ranking loss realize the order constraint. Matched, flipped, mismatched features are closer to the image feature in that order. We compare the proposed method with baseline methods representing different pretext tasks. Proposed achieved higher scores than baselines, which indicates that the proposed method can learn both audiovisual semantic and spatial relationships. We also showed the qualitative comparison. This is an example of image-to-sound cross-modal retrieval. Input is the image in which trumpet player on the left and the proposed method retrieves sounds of trumpet on the left better than baselines. This is an example of sound-to-image retrieval. The proposed method is also effective. We have proposed self-supervised method based on sound category and location. We have applied our method to cross-modal retrieval in stereo-recorded videos and showed the effectiveness. Future work includes extending our method to other tasks, such as sound localization. Thank you.
So moving on to the next paper, its title is Estimating Individual A Cappella Voices in Music Videos with Syncing Faces. Just a reminder to post your questions in the chat, and just after this paper, we'll have the first Q&A session.
Hi, I am Venkatesh, and I would like to present our work on estimating individual a cappella voices in music videos with singing faces. It is a joint work with Juan and Gloria from Universitat Pompeu Fabra. Our goal is to estimate the voice of a target face in music videos with singing faces. The visual information can be particularly useful when the target singer's voice has a low volume level or when there are overlapping singing voices in the mix. Though the research in audiovisual speech separation has gained a lot of traction in the recent years, the audiovisual singing voice separation remains a relatively unexplored research topic. Since there were no public datasets for audiovisual singing voice separation, we created a dataset called a cappella by putting together around 46 hours of a cappella solo singing videos sourced from YouTube. The dataset covers singing content in 4 language categories. The test set is segregated based on seen singers and unseen singers. The dataset is publicly available. It can be used for research in audiovisual singing voice separation and singing style transfer. Detailed dataset stats can be found on the project page. Next, we present our model architecture, YNet, which forms the basis of our models in this work. YNet is a 2-stream CNN for processing visual information and audio. The audio network is a 4-block unit. The visual network extracts motion features. The visual features and the audio network's latent feature are aligned temporally and fused together through film conditioning. YNet-M is basically a unit conditioned on the sequence of faces cropped around the mouth region. YNet-E is a unit conditioned on the sequence of face embeddings instead. It uses the visual network of LLCP model. For the baselines, we consider a 4-block unit as the audio-only baseline and LLCP, a state-of-the-art audio-visual speech separation model. We employ a mix and separate self-supervised training procedure. In the one lead voice setup, an a cappella dataset sample is randomly mixed with the sample from AudioSet or MuseDB18. Note that the models YNet-M, YNet-E, LLCP, and UNet are trained on samples obtained using this setup. In 2 lead voices setup, we have an additional voice in the mix. Note that the visual input always corresponds to the target singer only. With this, we introduce another model, YNet-R, which is same as YNet-M, but it is trained with 50% of samples having 2 lead voices. Here, we show some results on the unseen singers evaluated in 2 lead voices setup. To mimic the real-world multi-voice a cappella videos, we also recorded a multi-voice a cappella video so that we could report quantitative metrics using the individual ground truth voices. Note that the YNet performs the best in terms of SDR. From this, we infer that YNet generalizes well in unseen singers, unseen languages, and real-world multi-voice mixtures. Here's a demo on real-world multi-voice a cappella sample. Focus on the top right face while listening to the video. Note that this is an unseen singer.
Oh, isn't she pretty?
Note that our YNet YAM estimate is clearly better than the rest. In summary, we introduce a new dataset of a cappella solo performances. We propose a new audiovisual singing voice separation model based on a unit conditioned on the lip motion of the target singer. The audiovisual methods improve upon the audio-only method in challenging scenarios. Our method outperforms the baseline models in terms of SDR in separating a target singing voice in the two lead voices setup. Thank you. For more videos, please visit our project page.
Okay, moving on to the Q&A, Arsha.
Yeah, great. Those 4 papers are really great. So thank you to everyone who presented. So we have some questions in the chat from Valentina for paper 3. How do you correctly choose the margin for the different triplet losses? Do we have
Thank you for the question. I'm the author of the paper 3. And the question is how to choose correctly margin for the different triplet losses. In this experiment, we performed L2 normalization on the image feature and 3 types of stereo sound features. In this example, then we applied empirically known margins for the L2 normalized feature space. Specifically, we take a margin as 0.2. Thank you.
Great, thanks. Do you have a follow-up, Valentina?
Yes, I have not understood very well the formulas because they were shown very fastly. I don't know if you can go to the slide of the formulas of the triplet loss. Is it possible?
I think it might be a bit tricky because it's in a video form.
Okay. Because I have not understood very well the fact of the smaller distance with the flipped sound and the bigger distance with the completely different sound, let's say. So how to handle these 2 cases with the triplet loss, because usually in the triplet loss there is positive, negative, and margin. In this case, let's say we have 2 different kinds of negatives, the easier and the hardest. So I have not seen very well the formula, but I thought that there were 2 margins. So how it works exactly?
Thank you for the question. We use in we make the stereo locking loss in the same way as the triplet loss. So we we add the hard negative. We simply added hard negative samples to the triplet loss is 2. But our operation study showed that each losses is effective in the stereo sound ranking loss. So I think this making loss function is I think effective. Thank you.
Okay, thank you.
Thanks. So moving to the next question we have for paper 4, is it more difficult with never seen singers or never seen languages?
Hello. Thank you for the question, Valentina. This is Venkatesh. So yes, the never seen singer, since it is not covered during the training, yeah, is a bit difficult. It doesn't perform well on never seen singers, and we also have a separate set of results for the test seen singers, and we noticed that there is performance degradation in unseen singers. And yes, I hope that answers your question.
So also you tried to train on one language and test on a different language, so unseen language. So to see the, let's say, the drop in accuracy when you test on a new language, and instead when you train on a singer and test on a new singer, so the drop is bigger on a new singer, let's say, correct?
Yeah. Right. Also on the unseen languages, there was a table in the presentation. So in that table, we showed that in unseen languages, the performance is clearly lower than English, which is a major part of our dataset.
Okay, nice, thank you.
Okay, so just quickly moving on, we have a question from Siddharth for paper 2. What is the time taken to generate such videos at inference time, and what is the GPU consumption?
Hi, hello. I'm the author of paper 2, and of course, the time would be different on different GPUs, and actually we haven't calculated the time, but it's definitely slower than real time. On the other hand, our code is actually publicly available, so it's better for you to try it for yourself. And the GPU consumption for testing, of course, you can use a single GPU to generate the results. And for training, we use actually 8 Tesla V100 GPUs for training. Thank you.
Great, thanks. And we have another question from Kranti for paper 4. How different is singing from speech? And do you think pre-training on large-scale speech data will improve the performance?
Yeah, thank you for the question. The singing is clearly different from the speech in the sense that there are sustained vowels, and also there is this concept of pitch, which is more, there's a lot of musical content in singing voice, and is more complex than speech. But it is interesting that we should definitely consider how a model pre-trained on large-scale speech dataset could perform. We used LLCP model, but we trained it from the scratch on our dataset. So it didn't seem to perform as good as our models in multi-voice cases. But as you say, it will be interesting to try starting with the pre-trained model, pre-trained speech, source of speech separation model pre-trained on a large-scale speech dataset. Thank you.
Great, thanks. And then actually I had one question for Valentina for the first paper. I was just wondering, so you use only a single RGB frame as input to your model, right? Do you think that adding in maybe multiple frames would help with the localization? For example, when the man's about to clap, with that example, maybe having more frames would be useful.
Yeah, I used one frame to have the correspondence with the relative acoustic image, because we have a device that collects 12 acoustic images in a second. So in that case, we should consider 1 second of video and 1 second of audio. But the problem is that if we want to reconstruct the single acoustic image, we have just for 1/12 of a second. So either we make a mean, or we use just one, but we must know in which one there was the sound. Because let's say only one of the 12 acoustic images have the sound, the instant where the boy is clapping. All the other 11 instead have only background noise. So it's a problem. or you make some convolution to fuse them in some manner. In my case, I choose to use one frame for having the correspondence with the relative acoustic image. So that was the reason. And handling many frames, you will lose the synchronization, let's say, with the acoustic image.
Right, yeah, that makes sense. Thank you. So do we have any more questions? I think we have time for one more. If you have any, please post them in the chat. Or maybe wait a few more seconds. Okay, I think we're good. We don't seem to have any more. I actually had one more if we have time for Venkatesh for the a cappella. I was just wondering, what are the applications of separating out one singer? Do you think it'd be useful for like maybe education or?
Yeah, so thank you for the question. So there can be multiple use cases of this kind of model. Yes, certainly it could be useful for music education in the sense that when there are multiple voices, singing voices, if the evaluator wants to evaluate every individual singer, they could, in a music school, for example, it can be useful.
Right. Okay, and a quick question from Valentina. Do you think it's possible to separate both the singers and the instruments?
Our data set is not trained on instrument motion. So basically our models are trained to capture the lip motion. So of course, if we separate the voice, what remains is accompaniment. And we did run some tests on single voice and accompaniment separation. So in that sense, it works on instruments as well, which are a part of the accompaniment. But to single out a single instrument, we didn't train it that way. So it is something that we need to explore.
Great, thank you. So I think with that, we can move on to the next session. Thank you once again to all the presenters for this round. Let's move on.
Great. Okay, so let's move on to the next paper. So this is paper number 5. Title is Spoken ObjectNet, a bias-controlled spoken caption dataset.
Hi, I'm Andrew Duchenko, and today I'll be presenting our paper, Spoken ObjectNet, a bias-controlled spoken caption dataset, which has been accepted to Interspeech 2021. This is joint work with the following authors. We consider audiovisual models that learn from spoken captions of images. The main motivation for this research is to enable systems for language acquisition and object recognition in different languages. There are over 7,000 spoken languages in the world, but automatic speech recognition is supported by less than 2% of them, in part due to the large amount of labeled speech data required for each language. Learning from images and spoken captions instead has been shown to enable audiovisual systems that can understand words and relate them to visual objects. The Places audio captions dataset is one of the largest spoken caption datasets. Spoken captions were collected via Amazon Mechanical Turk. Here we can see some example images, the audio of the spoken captions, and the transcripts from the automatic speech recognition system. In our work, we are interested in extending the types of objects and scenes that these audiovisual systems can reason about. Therefore, we collected spoken captions of the images in the ObjectNet dataset. The ObjectNet dataset was proposed as an image dataset with controls on rotation, background, and viewpoints. Here we can see the difference in how chairs are photographed in ImageNet versus ObjectNet. We collected spoken captions for ObjectNet using Amazon Mechanical Turk. Workers were asked to describe shapes, objects, locations, and colors of the images. We used the speech recognition system to count the number of words and rejected recordings without words in real time. We introduced a novel step of using a BERT model with a language modeling head to assign a score to each caption and to reject poorly formed captions. Workers were also prohibited from captioning more than 12K images to prevent speaker bias. In the end, we collected around 50,000 spoken captions, with about 48,000 in the training set, 1,000 in the validation set, and 1,000 in the evaluation set. We split the data such that there's no speaker overlap between any of the sets. In total, there's about 155 hours of audio and about 18,000 unique words. Here we show sample images, audio of the spoken captions, and the automatic speech recognition transcripts from Spoken ObjectNet. Spoken ObjectNet is designed to be a test dataset for audiovisual models. To use the dataset, we suggest training an audiovisual model on some other dataset first. Then evaluate image audio retrieval on the evaluation set of 1,000 pairs of images and spoken captions. ObjectNet license prohibits the training of model parameters on the images. Therefore, only embedding layers in the audio model can be fine-tuned on our training set. We conducted transfer learning experiments from a model trained on Places audio. In the zero-shot setting, the model's mean recall attempt performance decreases from 0.735 on Places to 0.118 on Spoken ObjectNet. This shows that the model trained on Places can be directly applied to Spoken ObjectNet, but the performance is much lower. Fine-tuning the model with a frozen image branch recovers some of the performance, up to a 0.214 mean recall attempt. Here we show example retrieval results for two sample query images. In the first example, for the given image, the model retrieves the correct audio caption as the top result. However, for both images, the relevance of the other retrieved audio captions could be improved. To summarize, spoken caption datasets can be used to learn audiovisual representations without manually transcribed speech. We collected a new dataset of spoken captions based on the ObjectNet dataset, which has controls for rotation, background, and viewpoints. Our transfer learning experiments show that the current retrieval performance is much lower on Spoken ObjectNet than on Places audio. Future work may include text-based captioning experiments. Here are additional acknowledgements. Thank you for your attention. Hi, I'm Andrew Duchenko, and today I'll be presenting.
Sorry about that. Just one comment. I think Andrew Rychenko is not here, so you can send any questions you have offline by email. And let's move to the next one. I think it's from the same author. So the name is Cascaded. So this is paper number 6. And the name is Cascaded Multilingual Audiovisual Learning from Videos.
Hi, I'm Andrew Duchenko, and today I'll be presenting our paper, Cascaded Multilingual Audiovisual Learning from Videos, which has been accepted to Interspeech 2021. This is joint work with the following authors. We explore self-supervised audio-video learning from instructional videos, which contain visually rich descriptive language. We use the AVLNet model to learn a joint audiovisual embedding space from the raw audio and visual channels in instructional videos. Our goal is to learn from the raw speech audio instead of text from automatic speech recognition systems for several reasons. There are over 7,000 languages spoken worldwide, but automatic speech recognition is only supported for less than 2% of them. Automatic speech recognition makes errors for audio with background sounds, reverb, and accents, all of which are found in instructional videos. Also, learning from text misses the opportunity to learn from visually relevant non-speech sounds. The AVLNet model was trained on the How to 100 Million dataset, which contains 1.2 million instructional videos. It could successfully perform audio-video retrieval on the UCOOK2 dataset. Next, I'll present some audio-video retrieval results on UCOOK2 using AVLNet. The model only uses raw audio as input to retrieve similar visual clips without using text.
All right, so here's my flour mixture. I'm just going to add in some salt and some black pepper. You got to have black pepper. Yes, yes, yes. Lots of black pepper and some celery salt, just like.
In this example, the input audio query mentioned ingredients like flour, salt, and pepper, and the top 5 most similar visual clips all show similar ingredients. This shows that the AVLNet model can recognize spoken words and relate them to relevant visual content in videos. In this work, we're interested in learning representations for videos in other languages. However, there are several challenges. While there are many instructional videos available in English, there are not as many available in other languages. For example, there could only be hundreds of thousands for Japanese and only thousands for a low-resource language like Igbo. This is important because we find that hundreds of thousands of videos are necessary to learn strong representations. Even if there were large-scale datasets of videos available for all languages, it would be challenging to download and process them to train models given the significant engineering effort required. Therefore, in this paper, we propose a cascaded approach to learning multilingual representations. We use the AVLNet model trained on English videos and apply it to audiovisual data in other languages. We test this approach on Japanese cooking videos and spoken captions of images in Japanese and Hindi. In both cases, we find that retrieval performance significantly improves compared to training only on the Japanese or Hindi data. We call this a cascaded approach because the model learns from one language at a time. For example, first English videos and then Japanese videos. We collected a dataset of Japanese cooking videos. We call it YouCook Japanese to indicate the similarity in size and style to the English YouCook 2 videos. We consider the same task of audio-video retrieval, where the input audio queries are now in Japanese. In this figure, we show example zero-shot retrieval results of the AVLNet model trained on English how to 100 million videos and evaluated on the YouCook Japanese videos. We show the audio, Japanese text transcripts from an automatic speech recognition system, and the English translation. Even though the model has been trained only on English videos, it can still perform retrieval surprisingly well using natural sounds, such as sizzling and microwave beeps. When we fine-tune the model on the Japanese cooking videos, the retrieval performance improves. We can see that the model can handle more complex audio queries in Japanese and retrieve video clips with specific ingredients mentioned in the queries, like cheese, chicken, and cabbage. We also use our cascaded approach to fine-tune the AVLNet model trained on English videos on spoken captions of images in Hindi and Japanese. Here we show an example image with the spoken caption in Hindi and Japanese, as well as the corresponding output from an automatic speech recognition system, as well as the English translation. We find that our cascaded approach significantly improves performance on audio image retrieval using the spoken captions in Japanese and Hindi. To summarize, we proposed a cascaded approach to learning multilingual representations by using the AVLNet model trained on English how to 100 million videos and applying it to audiovisual data in other languages, such as videos in Japanese and spoken captions of images in Japanese and Hindi. We collected a dataset of Japanese cooking videos called YouCook Japanese, which is similar in content and size to YouCook 2. Our cascaded approach significantly improves performance on both audio, video, and audio image retrieval. The project resources will be released at avlnet.csel.mit.edu. Thank you for your attention.
Okay, sorry, apologies. Actually, Andre is here, so he can take questions. So please keep them.
I'm Andrew Duchenko.
Keep them coming for basically all the papers, and including the last two. So moving on to paper number 7. This is called end-to-end video-to-speech synthesis using generative adversarial networks with multiple critics.
Hi, everyone. Today, I'm going to be presenting our work on end-to-end video-to-speech synthesis using generative adversarial networks, or GANs. I believe most viewers should be familiar with the task of lip reading, where the idea is basically to transcribe speech directly from video. This can be seen as basically video-to-text translation. So in this work, instead of video to text, we actually want to do video to speech or video to audio. So we want to generate audio directly from silent video. This has 3 main advantages when compared to lip reading. First of all, it can be applied in real time without the need for the delay of waiting for each word to be produced. So instead, we can just produce a constant audio stream that has no delays on its pipeline, and that can be paired seamlessly with the video. Secondly, producing speech directly allows us to encode some of the important aspects of the visual speech that could not be encoded through text easily. These include emotion and intonation, for example. And finally, and perhaps most importantly, we don't require transcribed datasets in order to train our video-to-speech model, meaning that we don't need the text of what was said in the video for our data. And this is important because this text is typically expensive to produce or very hard to find. One of the applications that we've kept in mind throughout our work is the idea of speech imprinting, which basically means filling in the missing audio in an audio-visual stream. So in our case, we could just reproduce the audio directly from the corresponding video. This would be particularly useful, for example, in video conferencing, where the audio is frequently noisy or missing. And secondly, another application which has received some attention recently is the idea of helping people with aphonia, so people that cannot produce voiced sounds. So we could just point a camera at them and reproduce their speech. So this is a summarized view of our model. Basically, our generator is composed of a ResNet 18 based visual encoder, which then feeds into a temporal encoder, which aims to temporally correlate the visual features. And in our case, this is a bidirectional GRU RNN. And finally, we have a waveform decoder, which decodes these visual features into chunks of waveform audio, which are concatenated to make the full audio clip. For our critics, one of our main proposals in this work is that instead of only using a waveform critic, which is typical in video-to-speech synthesis, actually we also use a spectrogram critic, which learns to discriminate between the spectrograms extracted from the real and synthesized waveforms. So our losses are a combination between adversarial losses, which are based on the improved Wasserstein loss, and which aim to ensure realism in our generated samples. And these are also combined with 3 comparative losses, which aim to make sure that the content of the real and synthesized audio actually matches between the two. So here are some results on a somewhat simple data set, which is grid. I'm going to show the real audio first and then the synthesized one.
Bin white at T3 soon.
Bin green at E2 now.
Bin white with U0 soon.
Bin red at M0 soon.
Okay, and now for the speech reconstructed using our model from silent video only.
Bin white at E3 soon.
Bin green at E2 now.
Bin white with U0 soon.
Bin red at M0 soon.
And I also wanted to show some samples for a more challenging data set, in this case, lip reading in the wild.
That are already available.
David Cameron insists by everyone in this.
The government has already.
David Cameron insisted by everyone being.
The government has.
So you can see that it's intelligible, although not perfect. We compared with other works, and we show that we outperform previous works on most objective audio metrics. You can check the full results in our paper. And yeah, that's basically it. All of our samples are available on our project website, and our full study, including some extensive ablation studies of some of the choices that we mentioned before, is also publicly available on Archive. So yeah, thank you very much for watching our presentation. Hi, everyone.
So moving on to paper number 8. The title is Neural Dubber, Dubbing for Silent Videos According to Scripts.
Hello everyone, I'm Chen-Xu Hu. Today I'm going to introduce our new work, Neural Dubber, Dubbing for Silent Videos According to Scripts. This work is done by Mars Lab in Tsinghua University and ByteDance AI Lab. Dubbing is a post-production process of re-recording actors' dialogues in a controlled environment, which is extensively used in filmmaking and video production. While dubbing is an impressive ability of professional voice actors, we aim to achieve this ability computationally. In this work, we propose a novel task, silent video dubbing, SVD, which aims to synthesizing human speech that is temporally synchronized with the given silent video according to the corresponding text. The main challenges of the SVD task are twofold. The first one is temporal synchronization between the synthesized speech and video. The other one is that the content of the speech should be consistent with the input text. We introduced Neural Dubber, the first model to solve the SVD task.
Neurodubber is a multimodal speech synthesis model which generates high-quality and lip-synced speech from the given text and silent video. First, we apply a phoneme encoder and a video encoder to process the phonemes and video frames, respectively. Then we use the text-video aligner, which adopts an attention module between the video frames and phonemes, and then upsample the text-video context sequence according to the length ratio between male spectrograms and video frames. Finally, we use variance adapter to add some variance information, and then use the male spectrogram decoder to output male spectrograms. We propose the image-based speaker embedding module, which aims to synthesize speech with a reasonable timbre that is consistent with the speaker's facial features in the multi-speaker setting. That is achieved by taking advantage of the natural co-occurrence of faces and speech in videos without the supervision of speaker identity. We conduct experiments on the chemistry lecture dataset for the single speaker SVD and the lip reading SNS2 dataset for the multi-speaker SVD. The results of extensive quantitative and qualitative evaluations show that, in terms of speech quality, Neurodubber is on par with SOTA TTS models in single speaker setting, even outperforms FastSpeech 2 in a big margin in multi-speaker setting. Most importantly, Neurodubber can synthesize speech temporally synchronized with the lip movement in video. Let's see some results. Please pay attention to the lip movement of the speaker.
Well, let's just calculate from the ideal gas law. Well, let's just calculate from the ideal gas law. Well, let's just calculate from the ideal gas law. Well, let's just calculate from the ideal gas law. Well, let's just calculate from the ideal gas law. Now, when you have a mixture, each gas behaves like it has the whole volume to itself. So, now when you have a mixture, each gas behaves like it has the whole volume to itself. So, now when you have a picture, each gas behaves like it has the whole volume to itself. So,
here are the results for the multi-speaker SVD.
Who knew that one man? Who knew that one man?
Who knew that one man?
Who knew that one man?
That's the best kind of teaching. That's the best kind of teaching.
That's the best kind of teaching.
That's the best kind of teaching.
We can change the face image to alter the timbre of speech.
Did they get it done on time and for the right money?
Did they get it done on time and for the right money? Did they get it done on time and for the right money?
Did they get it done on time and for the right money?
Did they get it done on time and for the right money? Did they get it done on time and for the right money?
Here is the ablation study for ISE.
Exercise is a waste of time. Exercise is a waste of time. 10 favorite dishes that I cook.
10 favorite dishes I cook.
Made in a local factory. Made in a local factory.
An interesting thing is that the model trained on multi-speaker dataset can adapt to unseen speaker.
Each gas behaving like the other gas is not even there.
Each gas behaving like the other gas is not even there. Each gas behaving like the other gas is not even there.
Thank you for watching.
Okay, great. So moving on to the second QA, please post questions into the chat. So we have a question for paper 6, which is the cascaded multilingual audiovisual learning. And the question is, can your model be used to translate the caption of a video?
Hi, can you hear me?
Yeah.
Hi, thanks for your question. So the model we used only uses speech audio and video without using text. So given the speech in one language, it could be used to retrieve speech audio in another language. So it can perform audio to audio translation in a way. And this could be useful for languages where there's no automatic speech recognition or for languages that don't even have a written form. But I think future work could involve using text as well for a more direct form of translation. Thank you.
Okay, yes, thank you. I was asking, yes, the translation in the speech the audio translation, let's say. So it can perform the retrieval and then retrieve the correct audio in another language, let's say.
So we don't have quantitative results in our paper, but I would say qualitatively it could be. I would say the translation capabilities right now maybe aren't as good as like text-based translation, but it could be used to identify like visually relevant words like different ingredients, for example. It could retrieve audio in different languages. Yeah. So I guess basic words for now.
Okay. Thank you.
Great. So while we're waiting for more questions, I actually had a question for you, Andrew, for the first paper, which is Spoken ObjectNet. What do you think the advantage of spoken captions are over written captions? Do you think maybe there could be some bias in the identity of the speaker or other, aspects of their voice?
So I think one of the advantages with spoken captions is that they're just easier and more natural to collect than text-based captions. People are more adapted to describing things with their speech. So in terms of just collecting data sets, they're pretty, I would say it's, I think there's studies that show that it's faster to collect than text-based. So if the end goal is to collect text-based, it still seems like a good idea to collect speech-based and then perhaps use like automatic speech recognition to transcribe. I would say, as I mentioned, one of the motivations for our work is to build speech systems that can learn from unsupervised data that doesn't require like manually transcribed speech with text. So that's one of the motivations for our work to, can you just drop a system down like a robot maybe that just interacts with people maybe that are talking about different things, and to see whether we can connect the spoken audio to the images. And I think that's an exciting area because so far the speech has been like pretty clean. Like there's not a lot of background noise or like the cocktail party effect. But I think if we can build systems that can like reason both about the speech that people are talking about and also separate the the background sounds, that'd be pretty cool. So that's what I think are the advantages to that.
Right. That makes a lot of sense. Thank you.
Yeah, if I can add something, I think in ECCV I saw a dataset where there were annotations also where the people were describing what was in the scene, also using a mouse and moving the cursor to the different objects. So I don't know, describing a woman and pointing to the woman. So maybe that can be useful in your case.
Exactly. For anyone interested, that paper is called Localized Narratives.
Yeah, I didn't remember the title, but I remember that they were describing by voice, so it's something related, I think.
Great, thanks. Yeah, maybe we'll just wait a few more minutes for some questions. In the meantime, I had a question for the end-to-end video-to-speech synthesis, which is paper number 7. And my question was, have you tried training on the entire face images and not just the cropped mouth regions? And do you think that would help?
Okay, so hi everyone. I hope everybody can hear me. Yeah, so we have actually, that's one of the ablations that we present in our full study that's available on arXiv, as I said. And actually we find that it performs very slightly worse. There is also a study in the lib2f paper, which I compared with and referenced, where they actually look at the attention maps of where the network is looking at in the face to produce the speech. And obviously it's like very, very lip focused. But we think that in the future, I think especially with emotional data sets, the full face can have definite advantages. And of course, if the network was perfect in a sense, I suppose the face could have some intuitions. But yeah, for the purposes of our work, we tested that and we found that the cropped mouth works better because the network could just focus on that important part.
Yeah,
so thank you for the question.
Yeah, that makes a lot of sense. I guess the full face could be useful when maybe the mouth is occluded or,
yeah, exactly, yeah.
Great, thanks.
Thank you.
Does anyone else have any more questions?
Can I ask one more question to Rodrigo since he's
yeah.
here?
Yeah,
great paper, by the way. Like super impressive results, and I think so. You showed some results on LRS2, which I assume that the models there were not tailored to a specific speaker, right? So you had it was like speaker independent.
Yeah, we showed on LRW actually, not LRS2.
LRW, but same, right? Like you didn't have like you didn't tailor those to a specific speaker, right? Because this is a bit like more broad question, isn't like my understanding from looking at those papers, like also like from your results. It seems that when you tailor those models to a specific speaker, they work incredibly well, but it seems that there is still it's still quite challenging to get them to generalize very well for you know, like any unseen speakers. Do you have any idea like what, you know, like what the most important thing that needs to be solved there is to actually get good results on unseen speakers? Like what the greatest challenge is there?
Yeah. This is actually one of the main things that we're approaching in our new video to audio work, which we haven't released yet, but we're working on it quite hard. Basically, I think, so the obvious thing that's missing here, which is actually present in some other video to audio works, I think Lip2App is a good example, is using a speaker embedding, right? So instead of only fitting in the video, use a speaker embedding. Of course, that brings up the issue of like, okay, how do you get, first of all, an unbiased speaker embedding that is not biased by being produced from the same sample? There's the fact that speaker embeddings are actually typically used for speaker verification, so they're not as complete as you would think in order to actually reproduce the person's speech, although for Tacotron 2 multi-speaker speech synthesis, it seems to work well. I think that obviously the main step forward is to actually condition it on speaker embeddings, which is something that we're planning to do. But also, I think that in general, it's difficult to find very good speaker embeddings, and it basically requires training a very good speaker embedding encoder. And that's really, I think, where the focus is if you want to get really good unseen speaker performance. And also, you know, the model needs to be really good, right? Because, you know, it's not only that you need to know the voice, it's also that you need to be able to read lips in a generalizable way. And as has been pointed out in other papers, you know, individual speaking styles are actually substantially different in nature. So yeah, I think it's about, you know, getting a better video to speech model, which is a more general thing, and also getting speaker embeddings to condition on and getting them as good as possible, which is not as trivial a task as one would think, I think. So yeah, I think that's
great. Thank you.
Thank you.
Okay, I had one last question actually for paper 8, which was the neural dubber. So my question was, a very popular application obviously seems to be dubbing video to other languages. And so how challenging do you think this would be? Obviously the lip sync would be, you know, totally not possible, but maybe a best estimate to make it seem natural. So what are your thoughts on that?
Hello. I'm the author of paper 8. Could you repeat your questions because I didn't hear it clear?
Yeah, no worries. No, my question was, do you think this would work for dubbing in different languages?
Yeah. For now, I think if we need to dub for another language, we need a speech synthesis model for the other language. So we need another language's data set to train it. But now we only test on the English, and the video and audio is all impaired and all in English. So we left it for future work. We aim to dub the English video and to generate maybe Chinese and other audios. We left it for future work.
Great, that would be really interesting. Thank you so much. Okay, great. So of course, if you have any questions, feel free to contact the authors later as well. But I think with that, we can move on to the next session. So thank you to all the presenters once again. for these great presentations.
Okay, great. Let's move on. Okay, so moving on to paper number 9, learning representations from audiovisual spatial alignment.
Hi everyone, my name is Yi Li, and I'm presenting our work, Learning Representations from Audiovisual Spatial Alignment. This is a joint work by myself, Pedro Morgado, and Nuno Vasconcelos. Humans experience the world through multiple senses. Through the multisensory neurons in our brains, we're able to integrate information from signals of different modalities, such as images and sound. This allows us to draw correspondences between co-occurring audio and visual signals. For example, we can easily associate the sound of musical instruments, animals, cars, and the ocean with their visual appearances. This tight correspondence between visual and audio modalities does provide a strong signal for self-supervised representation learning. Specifically, audio and video neural networks can be trained to identify audio-visual correspondences. If an audio and video pair is from the same sample, then the pair is considered a positive correspondence. Otherwise, the pair is considered a negative correspondence. This task is in fact the basis of several recent works, which show strong results on downstream tasks like action recognition. However, in these methods, the audio is used as a descriptor for the whole video. As a result, the learned representations struggle to discriminate visual concepts that often co-occur. In the natural world, however, both audio and visual signals are often well localized. In this example, we can easily locate the relative position of the waves in relation to us even without looking. The ability to locate sound sources from audio alone can thus be used to disambiguate co-occurring visual concepts. In this work, we showed that reasoning about the spatial location of sounds enhances representation learning. We accomplish this by learning to spatially align audio and video clips. Consider the 360 video environment exemplified in this slide, which contains a person talking, a car running, and a building. From this 360 video, we can easily extract audio and video clips from multiple viewpoints. We then pose audio-visual spatial alignment as a contrastive learning problem, where audio and video pairs from the same location are treated as positives and pairs from different locations as negatives. All video and audio clips are first independently processed by the video and audio encoders, respectively. The loss could potentially be imposed on these representations. However, we showed that we can further enhance the ability to perform spatial alignment by reasoning over the full spatial content of the 360 video, using a transformer architecture to combine representations from multiple viewpoints. Audio and video clips from the same viewpoints are finally matched using a contrastive loss. Here's a closer look at the cross-modal transformer architecture, which consists of a stack of layers alternating between self-attention over all viewpoints and a simple clip-wise transformation. In order to learn from audio-visual spatial alignment, we collected a 360 video dataset with spatial audio. The dataset, which we call YouTube 360, contains over 200 hours of content with clips from a diverse set of topics such as musical performances, vlogs, sports, and others. After training on our dataset, we compared spatial alignment pre-training with prior work on audio-visual correspondence learning. We found that combining spatial alignment with correspondence learning significantly improves over correspondence learning alone, not only on the spatial alignment task, but surprisingly on the audio-visual correspondence task as well. We also showed that spatial alignment enhances the transfer performance for semantic segmentation and action recognition downstream tasks. For detailed results, please check out our paper. Dataset code and models are available on GitHub in the link below. Thanks for watching.
Okay, so moving on to paper number 10, material converter, manipulating materials of visual objects with sound.
Hello everyone. Today I'm going to talk about our work, Material Converter, Manipulating Materials of Visual Objects with Sound. This is a joint work with Ting-Le Li, Yicheng Liu, Andrew Owens, and Han Zhao. So what is audiovisual material conversion task? Given a source video and target material audio as input, this task aims to convert the source video to a new video that corresponds to the target material audio. This is an example where water is converted to grass. Please note that we only want to convert the material texture of the visual object while preserving the structure of the source image, as similar to other image translation tasks. Now we will explain our material converter network in detail. In order to convert material texture while preserving the visual structure, we apply two distinct training objectives that are implemented as two discriminators. The first one is called audiovisual texture discriminator, which aims to convert the material texture from the source to the target material. It involves a GAN loss, which discriminates whether a pair of audio and video are correspondent or not. The second discriminator is called patchwise structure discriminator. It aims to preserve the structure of the converted videos. This can be achieved by matching the patches from the generated video to the input source video. In this given example, a generated grass patch in red should match its corresponding patch in blue, instead of other random patches. This setup can be easily implemented as a contrastive training objective, where the corresponding blue patch is the positive sample and the other random patches are the negative samples. We show some qualitative results here. As you can see, our input video is hitting or scratching water, and the input sound is hitting grass. We obtain the output video where the water paddle is converted to grass lawn. Another demo is to convert from water to gravel. As you can see here, the water region is effectively covered by gravel in the output video. As we highlight here, our material converter is able to generate different kinds of materials based on different sounds that are provided. In this case, various gravel sounds are generated based on different gravel sounds, which is a very interesting property that can be used for creating fancy demos in the future. We have also included failure cases here. In this scenario, when the given input sound is ambiguous, material converter might not be able to identify its targets, which leads to inferior conversion. An existing shortcoming of our material converter is that the irrelevant objects in the video are difficult to be retained. In this example, the arm that holds the drumstick is supposed to be retained at the conversion, but unfortunately, it did not happen. Here's another example where we can see a colorful arm in the converted video, which is not what we expected. Finally, our material converter might sometimes give the same output video for different input sounds. This will typically happen if the given audio embedding collapses. That's our presentation. Thanks for your time. Hello, everyone.
Okay, next paper. This is number 11, multimodal clustering networks for self-supervised learning from unlabeled videos.
Hi, I'm Brian Chen from Columbia University. Today, I want to present our work, Multimodal Clustering Network for Self-Supervised Learning from Unlabeled Videos. This work is done during my internship in IBM. The problem definition will be as followed. The input will be unlabeled videos along with their audio and ASR transcript. And we also assume that for across the three modalities, audio, video, and text, there should be something in common. For example, like the instructional videos, people will talk about what they are doing in the video. And the goal is to learn a unified representation in a common space for downstream multimodal tasks. So the common space features can be used for retrieval or action step localization. The key idea of this paper is to learn a common space by clustering multimodal features. For contrastive learning, it learns by pulling features across different modalities to be close when they co-occur in time and pushes those features away when they do not co-occur. But the limitation is those negative sampling doesn't consider the semantic. For example, if two videos are about cutting the onion, it might be pushed away because they do not co-occur in time. And for clustering method, it is done by clustering features that are close in semantic. But in current method, it only works on single modality clustering. So in our work, we want to perform clustering in a joint space across the three modalities. So in our work, we start from extracting features across the three modalities, and later we learn a projection layer to project them into a common space. In order to make the features across modality to be comparable, we apply pairwise contrastive loss and MMS loss to make the features to be directly comparable. And after that, we perform a multimodal clustering. It is done by calculating the mean feature across the three modalities. And later, we perform k-means on top of it. And after the k-means, we can get the centroid features. We view that as semantic centroid. And for each features, we want to make it to be closer to its semantic centroid and to be far away from the others. We also had a reconstruction loss to reconstruct the original features for regularization. After we learn the common space feature, we perform on two downstream tasks. The first one is text-to-video retrieval, which is given a text query, usually human written captions, and later we want to retrieve the correct videos from a large video pool set. And the next text is action step localization, which is given a long video along with its possible action steps. We want to find the temporal boundary of each action step in the long video. Our model achieves state-of-the-art in various multimodal tasks. We also compare to other baseline using the same feature extractor for fair comparison. We also done some ablation study and find the clustering to be essential for classification-related tasks like action step localization, since clustering makes semantic close instances to be closer. We also find joint space encourage semantic closeness from different modalities. And at the end, we find the audio to be crucial in our model because audio is informative in the cooking videos, and also we find audio can bridge the gap between the video and text, which is the largest gap across the three modalities. In conclusion, we propose a clustering network that learns a common embedding space by combining a contrastive loss along with a global clustering loss that learns semantic relation for a multimodal learning. An experiment shows that creating a joint space using video, audio, and language with a clustering loss could be beneficial in various downstream tasks. And we also hope that the method can extend to more modalities, such as optical floor or sentiment features, to learn without human annotation. Thanks for listening.
Okay, and moving on to paper number 12, depth-infused binaural audio generation using hierarchical cross-modal attention.
Hi, I'm Kranti. I'll present our work, Depth-Infused Binaural Audio Generation using Hierarchical Cross-Modal Attention. This work was done in collaboration with Neeraj Matiali, Siddharth Srivastav, and Gaurav Sharma. The sound we hear is binaural and has spatial properties, that is, we can guess the approximate location of the source. This is possible because our ears are at a distance apart and we hear a slightly different sound in both ears in terms of time and amplitude. This difference, both in terms of time and amplitude, is then exploited by your brain to infer the location of sound source. But this effect is lost when we record monaural audio with a single microphone. On the other hand, to record a binaural audio, we need a dummy head with microphones placed inside both the ears. But the problem with this setup is that it is bulky and not user-friendly. So the goal of this work is to convert mono audio to binaural audio conditioned on the visual signal. In order to perform a successful conversion, the system should consider the following. First, the system should locate different sound sources in the scene and model the relative separation between them. Second, it should account for the distance of sound sources from the recording device. Third, it should model the scene geometry for producing a realistic binaural audio consistent with the visual information. In the existing works, people have worked towards some of the requirements. In the first category of approaches, visual information in the form of RGB or optical flow images is fed to the network along with audio to get the binaural audio. In the second category of approach, the network takes the position and orientation of source and receiver both, which improves the performance. But this requires specialized hardware to track the position of source and receiver. Inspired by this recent observation of using position and orientation information, we use depth features as a proxy for both position information of source receiver and also the geometry of the scene. Here is the diagram of the proposed approach. We first extract audio features using a convolutional network. Then we give the corresponding image frame both to image and depth transformer network and obtain image and depth features. Both the features are then reset. Then we obtain a cosine similarity between the image audio and depth audio features respectively. This is the cross-modal attention to find relevant regions for both image and depth. Then we concatenate both the attention map along with audio features, and these features serve as input to the next convolutional layer. Then we perform strided convolution to get the features for next layer. Similar cross-modal attention is calculated for every decoder layer and is concatenated with audio features from the previous layer along with encoded features from corresponding encoder layer using skip connections. The attention calculation is done after aligning the number of feature channels for both image and depth with audio using a single layer neural network. Here are the results. We first saw quantitative results where we are close to the state of the art and are below the performance of the method, which either solves multiple tasks or has a better loss function. We also provide qualitative results for both visual and depth attention. We can observe here that for visual attention, the attention tries to better localize the sound source in the scene with increasing layers 2, 3, and 4. We also observe that layer 3 produces high values for the source on the right side of the image, whereas layer 4 produces high value for the source on the left side of the image. This region-specific attention map can be considered as the inherent association between left and right audio channel with left and right regions of the image, which is important for an effective binauralization. For depth attention map, we observe that high values are produced for different structures of the room instead of sound sources, such as the wall, ceiling, and floor. We can conclude that depth network is possibly looking at the geometry of the scene, which is also essential for binauralization. Finally, in conclusion, we propose a novel approach for audio binauralization by infusing depth features along with visual features. We propose a cross-modal attention at each decoder layer to associate information from all modalities at varying levels of details. And finally, we use a transformer backbone to extract both visual and depth features. Thank you for your attention.
Okay, great. So our third QA session. Thanks to all the presenters for those lovely talks. I see we have some conversations going on in the chat, so I'll just read out some of the questions, and this is for the people we're live streaming to as well. Feel free to answer again, and if you don't want to, that's also fine. I can read out the text answers. So we have a question from Valentina, which is for paper 10, is your architecture more similar to an image-to-image translation network or to a cycle GAN?
Hi, can you hear me?
Yes.
Yeah, okay, thanks for the question. And yeah, it's kind of similar to an image-to-image translation network, but we have also included audio in the network. And we think cycle GAN is actually one of our baseline models, and our model only involves one GAN, and it uses patch-wise contrastive learning to constrain the structure of the video. Yeah.
Okay, nice. Thank you.
Thanks. And then another question from Valentina is the model failing collapsing when the sounds are very similar?
Yeah, like it will probably collapse, but like if the sounds are too similar, or yeah, but then one of the other reasons could be that the learned audio embeddings are not as representative or are not as powerful as enough. So yeah, so that's what we thought.
Another question I would like to ask, have you tried this conversion just with the materials, also with some other kind of objects? I don't know.
Yeah, actually, that's one of our plans in the future, and we're going to collect more data. And yeah, because currently we're using Andrew Owens's the greatest hit dataset, and we have selected some of the useful things from there. So yeah, that's the current progress. But yeah, we will do some other materials in the future.
And do you think it would be more difficult with objects because, I don't know, for example, it's more easy to reconstruct a texture rather than a different object?
Yeah, I think that's true. Yeah, I think some objects are definitely easier. Like you can clearly hear the sound between the interactions. Like if you can hear the sound of the interactions of the object, but if the sounds are weak, it will probably give some weird behaviors, maybe. Yeah.
Okay, thank you. Very nice job.
Yeah, thank you.
Great. So I had a question about paper 9. So firstly, thank you for the great data set. It sounds like it'll be really useful. I was just wondering, how scalable do you think collecting this data set was? Do you think there are many of these like 360 videos on YouTube, or did you find that, you collected all the videos that were available?
Sorry, mute myself. Thanks for the question. Yeah, so this is actually one of the main concerns of our paper, which is that, to be honest, there hasn't been a huge or massive scale of 360 video, especially with spatial audio in the content, in like on YouTube or other sources, which is what our method relies on. But we do expect that with the newer hardware devices for capturing those videos and making these spatial audio recordings, it should be expected that people will continue to upload these 360 videos to the internet, and by that we can basically scale because the data collection process was rather straightforward. This is kind of a self-supervised method, right? So you don't need like having people annotate anything other than just some simple pre-processing of the videos. So the method should be quite scalable once more data becomes available.
Right. Yeah, that's a good point. It's kind of like something that will just only grow in the future. So, yeah, great. Thank you.
Thank you.
And then I think Daffy, did you have a question?
Yeah, I had a question for paper number 12. It's a bit more of like a technical detail. Just wondering. Great idea, by the way, like combining the depth for the binaural generation. I was just wondering how did you use pre-trained networks? I presume you did some pre-training for the image in the depth network. And were there just what were they pre-trained on? And like, did you have to freeze them and train the rest of the network on frozen features, or did you also have like a fine-tuning step in the end for doing that end-to-end? And same goes for like the audio network. It was also pre-trained, and what part of it was done end-to-end or not? Thanks.
Yeah. Okay. Hi. Thanks for the question. Yeah. Both I guess you're talking about the image and depth network, pre-training of image and depth network. Right? Yeah. Both of them were pre-trained. Like image network was pre-trained on ImageNet, and the depth network was pre-trained on Mix6 dataset. Like that is a large-scale depth dataset. It has around 1.4 million images, and both of them are also like trained in an end-to-end fashion.
So do you train end-to-end after the first, like, do you train end-to-end straight away, or do you do some curriculum where you first freeze the pre-trained networks?
No, we train it to end-to-end.
Interesting.
Like we tried fixing, but it didn't work, possibly due to the shift in domain.
Okay, makes sense. Thank you.
And then I had one last question, actually, for paper, I think it's 11. Yeah, paper 11. So once again, thanks for the great work. I was just wondering, sorry if I missed this, but how does the model perform without audio? So you mentioned that audio is like a bridge between the text and the video. So do you show results without it?
Hi, I'm Brian. Yeah, so in this work, we didn't show results without audio, but yeah, the model can definitely train with text and video only. So yeah, we just find like adding the audio will boost the performance a lot. And we also find like the gap between three modalities, video to audio, audio to text. The gap between video to text is the largest. So we thought that like adding audio will help like learning those common space representation.
Right, yeah, that makes sense. Okay.
Yeah, thank you.
Great. Thank you. Let's wait a few more seconds maybe for questions coming into the chat.
Can I just ask a question? Like, I think we're good on time. It's actually on for the paper number, the material converter anyway. I've forgotten like which numbers are. Could you give some intuition about the, like, I think this is relatively related to what Valentina was asking. Can you give some intuition about what the extra loss that you're using? The patch, like the contrastive one on the patch is like, so what would happen if you didn't use that? Is it just like the model is collapsing? So was it about like convergence, or is it just like worse qualitatively? Could you give like us an idea like what exactly this improves?
Yeah, okay. So for the intuitive understanding, like the reason why we use the patchwise contrastive learning loss is because we have considered the image to contain, or the video to be like a two-part thing. The first part is a structure, and the second part is the texture. So we want to use the contrastive learning or the patchwise contrastive learning to how do you say, to maintain or to retain the structure of the image. So after conversion, the image won't just look something just weird. So that's the reason for it. So if you if you try to understand it as a psychogan thing, like for psychogan, yeah, they construct or they try to preserve the structure of the image or the video by using a reverse GAN, like a GAN backwards, and we just took away the backward GAN by just using a patchwise contrasted learning objective. That's the intuitive understanding.
I see. Okay, thank you.
Thank you.
Okay, great. So thanks to all the presenters from this round once again for these really great papers. And I think we can move on to the last and final session.
Great.
For this session, obviously, there's a whole day of talks. Yeah.
Right. So paper number 13, it's called Localizing Visual Sounds the Hard Way.
Hi, today I'm going to present Localizing Visual Sound the Hard Way. This is work done by Honglie Chen, Weidi Xie, Trentafilos Afros, Asha Nagrani, Andrea Vidaldi, and Andrew Zisman. Natural objects are often characterized more than just appearance, but also sound. For example, a dog barking or the sound of a hammer striking a nail. A full understanding of natural objects should not ignore their acoustic characteristics. Therefore, in this work, we consider the problem of localizing visual sound, i.e., the part that emits characteristic sounds. In this example here, we localize the sound source of this piano using our automatic negative mining techniques. We do this by thresholding the audio-visual heat map into a trimap. The trimap then defines objects, uncertain, and background regions. We use the background regions as extra hard negatives in our contrastive learning framework. In these slides, we then detail our training framework. In first part, given one frame and its corresponding audio, we firstly extract the visual and audio feature using CNNs and obtain a cross-modal correspondence score map. We then apply threshold to generate positive and negative regions in the second part. This forms a trimap shown here. The blue, green, red regions refers to negative ignore and positive regions respectively. During training, the negative region calculated from the background within the same image refers to hard negative, the easy negative coming from other images in the batch. We use the positive region here as our positive and ignore the uncertain region. Influence E loss is applied in our contrastive learning framework. Here, we show our trimap visualization during training. We use the object region as our positive and the background region from the same image as our hard negatives. We conduct experiments on two datasets, Flick SoundNet and the VGG Sound Source. The first one is a standard benchmark. However, as both the number of total instances and sounding object categories are limited, we introduce a new benchmark, VGG Sound Source, based on VGG Sound dataset. It contains more than 5K video clips across 200 classes. We show some example keyframes and their bounding box annotations. The second chart here shows number of bounding box per keyframe. Majority of them contain only one bounding box. The last chart here shows the area of object to area of the full frame. This indicates many sound sources are concentrated in the frame. We compare recent methods and various training sets on both test sets and show the improvement of our method. To test on Flickr SoundNet test set, we show models trained on small or large training set. Using 10K training data, our model shows 4% increase comparing to the previous state-of-the-art method. Switching to large training set, our model still shows better results. The right three bars shows model trained on VG sound and test on VG sound source. Our model still shows the best performance, but the value reduces largely. This indicates that the VG sound source is a much harder benchmark and can be used in future research. In the next two slides, I will show qualitative results on Flickr subnet testset and VG sound source testset. The first column shows images with annotations on. The following four columns shows different methods trained on different amount of training data. Thank you. Please visit our website for more results and pre-trained models and code.
Okay, and moving on to our last paper, this is paper number 14, Face to Music Translation.
Hello everyone, this work is about face to music translation. Learning a mapping between two unrelated domains such as image and audio without any supervision is a challenging task. For example, when we want to map human faces into musical instrument notes, finding a meaningful association between them is hard. In this work, we use a distance-preserving generative adversarial model to translate human face images into musical sounds while enforcing that the measured similarities between face images are proportional with those between translated audio samples. For example, the two visually similar face images wearing red hats are supposed to be mapped into audio samples which sound perceptually similar to each other. In the next slide, we'll describe our proposed method in detail. Our method first trains a neural network to embed faces into a metric space. In this metric space, the distance corresponds to a measure of face similarity. We then train a generative model that takes the face features and synthesizes raw audio waveforms. We use a generative adversarial learning approach to fit the output audio samples into a distribution of musical note sounds. The distribution here given by a public dataset in synth, which consists of musical note sounds recorded by 10 different instrument families. We then train a separate audio embedding network that maps the raw audio waveforms into a new metric space. In this metric space, the distance directly corresponds to a measure of audio similarity. This audio similarity is defined by our new hybrid audio metric, where the instrument family class information is incorporated together with the Mel frequency cepstral coefficients, i.e. MFCCs. This ensures that musical samples with the same musical instrument timbre are close to each other. We want the geometric structure of the face samples to be preserved as they're mapped into the audio embedding space. To do this, we enforce that the distance between any two input face samples is equal, up to a scaling constant, to the distance between the corresponding output audio samples. However, we discover that the distance preservation constraint in the generative adversarial model leads to reduced diversity in the translated audio samples. To address this, we propose to add an additional adversarial constraint, an auxiliary discriminative network. We found that this enhances the diversity of the translations generated when using the distance preservation constraint. Our evaluation metrics are Pearson correlation, that measures the metric preservation between pairwise distances of samples, and Frichet inception distance score, that measures the quality of the generated samples. And FID is also known to be sensitive to the variety of the generated samples. First, we see that Pearson correlation increases by adding the metric preservation loss. However, FID score increases as well, which means reduced quality in the samples. By adding the auxiliary discriminator to our model, we see FID score decreases again. Our t-SNE visualization of the audio metric space also demonstrates this. The red dots in the plot represent the translated audio clips. The blobs with 10 different colors represent real audio samples recorded by 10 instrument families. It is apparent that the distribution of red dots shrinks when the metric preservation loss is added. However, after adding the second discriminator, the translated samples are spread evenly over the real clusters, and we observed that the translations play a much wider variety of musical sounds. We also show the visualization of the face metric space. Our translation model with the auxiliary discriminator clearly shows the clusters by the assigned labels. This is a visual check to show that faces assigned to the same instrument class share visual attributes. For example, same skin tone, hair color, etc. Finally, this is a video demo of our result.
Oh, I think that was it. Okay.
Okay, moving on to questions. We have one question from Valentina for paper 13. So I guess Daffy, you could answer this one.
I can answer this.
So how do you find positive regions automatically?
So thanks, Valentina, for this question. Okay, the intuition for what the model does is both the positive and the negative regions, they're automatically discovered by the model during training due to the loss formulation that we have. So what we basically do is we take one image and with its corresponding ground truth audio, and we say that we want to match and not match this audio to this image. So the model has to find out for itself part of the images that will be negative and part of the image that will be positive. So this is like the only constraint we do, and we also add this intermediate, like this interval in between the negative and the positive, just because we want to have like this area we're not really sure if it's going to be positive or negative, so we want to give like the model some slack. And we don't really do anything else to enforce that. So we just train with this like in that way, and the model actually finds like a way to assign the background pixels to like negatives and assign like the foreground pixels to like positive loss part, like loss term, and this is how the model learns it. I hope this makes sense.
So let's say the network is refining itself automatically.
Exactly.
Okay.
Yeah, it's just like a self-training paradigm where like we get like pseudo labels, then the model learns with that and it keeps it. Yeah.
Okay.
And then one more question from Valentina, which is, do you think that using free shape automatic annotations rather than bounding boxes localization accuracy would be higher?
Related mostly to the new dataset with the bounding boxes. I mean.
So can you specify a bit when you say free shape automatic annotations? Do you mean more like something like proposals, like from a like a heuristic, like selective search or something like that, or do you mean like scribbles that people do?
No, like when a visual network is putting the attention on an object, for example.
Oh, you mean like from saliency then?
Yes, more or less. Yeah, using some kind of pre-trained visual network.
I see. Yeah, that's a great suggestion. So like we didn't really do anything besides that. Like again, like the idea was that you want to make it to get like let the model to try to figure this out for itself. This is a good suggestion. Like we haven't. I mean, I guess like the way to see if this would help is initially you can even start with like strong detector like outputs and see if guiding like really strongly the model to learn which like the positive and negatives areas are, like if this would help. And if it would, then we can like move on to doing something like less obviously like less supervised, like something like you mentioned. I'm just like I'm not very aware of many. I mean my understanding is like this is kind of like this is currently researched, but I think like most of like saliency methods are like actually not really they're usually weakly supervised, so you need to have like some notion of the object category. I think that
no, but I don't know exactly how you collected the annotations for the dataset, the new dataset for the testing. So how did you collect the bounding boxes, for example, with a pre-trained model, I think?
So is the question for testing? So for testing, we had to actually manually label about like 5,000 samples to just like make sure that they, just for the evaluation, to make sure that the evaluation is correct. But we don't use any of those during training.
No. Sorry, I was making confusion. So you collected new bounding boxes for a better evaluation, right?
Yes, we did, but just for the evaluation, for the testing.
So were they manual or automatically?
It was a semi-automatic pipeline. So we did use detectors initially to get us, because we knew roughly like the video class, and we did use a detector initially to give us like some detections, but then we went through them manually, and like we actually checked that they were correct.
Yeah. So my point was, instead of using a detector, finding instead a free shape region, so that maybe localization ground truth is more precise, rather than a square that is not fitting well the object.
Oh, I see. You mean instead of like having just like a bounding box, if we have tried segmentation maps.
Yes, exactly.
Well, the output of the model is actually something that it is a heat map. It is like a segmentation map.
Yeah, but the problem is that the ground truth is not like that.
Yeah, you're right. I mean, it obviously takes it's like much more effort to actually get like segmentation annotations. I agree with you. Ideally, you would want to have something like that, and like evaluate like that. But I mean, we also sort of like this is also like work that has been, it's on top of like other works that have been doing a similar thing, and it's the same thing with object detection and segmentation, right? It's like obviously you get something more, but it's like much harder to annotate. So, but it's a great suggestion. You might look into it.
Because you see, there is like a mismatch between the annotations and the output of the network, because the output of the network is not a bounding box, but the annotation is. So also that is making the accuracy lower, in my opinion.
Yeah, it's possible. It's possible that if you get to a place where your output maps are like so good and like are like detecting or highlighting the object like that well, that you actually lose something from that this will be an issue. But frankly, I'm not really sure if we're like there yet, especially with self-supervised methods. But this is a good point, definitely.
Thank you.
Cheers.
Great, thanks. And then I have one final question for paper 14, so the face to music translation. So thanks a lot. This is really a really creative idea. I was just wondering, because I don't think it was in the presentation, what would be like a practical application of mapping faces to musical notes?
Yeah, it's definitely a good question. So this work is related to, and there's another work where we do a different type of mapping of faces into an audio domain. So the main application would be for something called sensory substitution. The idea basically for visually impaired individuals to give them some way to receive visual information. And so these methods are holistic, so they don't break anything into parts, which can be appropriate for faces. At least part of our facial recognition system works holistically as opposed to by parts. And this can be possibly, we're working on ideas to combine this with other more spatial sensory substitution mechanisms.
Great, thanks. Yeah, that sounds like a really great noble application. So
thank you.
Thanks.
That's a great application.
Yeah. Okay, great. So I think with that, we've actually concluded this first session. Thank you to all the presenters for really great work. And yeah, stick around for the rest of the day since we've got a lot of exciting stuff coming up.
Thanks, everybody.